Hello, my name is Panos Koutsovasilis. I am from IBM Research Europe and I'm going to present to you our paper in CCGrid 2021 with the title A Holistic System Software Integration of Disaggregated Memory for Next Generation Cloud Infrastructures. We strongly believe that the next generation of cloud infrastructure will feature disaggregated resources. Some advantages of having disaggregated resources in the context of cloud infrastructures are that we achieve better resource utilization, lower total cost of ownership, higher energy efficiency, and we get unlocked hardware refresh cycles. Switching back to today's infrastructures, we observe that the combination of the growing memory demands and the vast variety of workloads present a great obstacle for cloud infrastructure providers. Providers target a perfect balance between computational power and memory within the boundaries of the single node. The available today solution to achieve this is node over-provisioning. As we see in this example, over-provisioning includes the overcommitting of resources, and specifically in the case of exceeding the available memory of the node, it utilizes these resources to make everything fit. However, this solution is not going to last as memory demand is increasing rapidly and no static over-provisioning can compensate for it. We believe that there is a more definite solution, and this is disaggregated memory. In the same scenario as before, when there is need for more memory, we can dynamically compose extra memory resources with disaggregated memory. In this way, we can adapt at runtime the resource of the node, compensating for any scenario. For the needs of disaggregated memory in our work, we use ThemesisFlow. ThemesisFlow is an open source framework for hardware memory disaggregation which provides not only the hardware but also a full out-of-band control plane as well as some basic integration with Linux memory subsystem. The first objective is to make the Linux manage disaggregated memory. To this end, ThemesisFlow exposes disaggregated memory to the Linux kernel via NUMA node 16. However, because at the boot time of the machine there is no disaggregated memory attached, ThemesisFlow exposes NUMA node through the device tree defined in the firmware with the flag usable memory set to 0. In this way, the Linux kernel won't try to access this memory at boot time and the machine can actually boot. However, with this flag in place, the Linux do not automatically fall back to disaggregated memory when the local memory is exhausted, and the kernel built-in mechanisms such as AutoNUMA do not support operation for this memory region. As it is now, in order to utilize disaggregated memory, we need to run everything with NUMActl and explicitly bind the process to the NUMA node 16. To bypass this limitation, we modified the firmware of ThemesisFlow and we reserved some small portion from the local memory that we expose through the same NUMA node 16. In this way, we can remove the usable memory flag of the NUMA node and make the Linux kernel manage automatically the disaggregated memory. Our next objective is to balance the memory pages by migrating the frequently accessed ones to local memory and demote the less frequently accessed to disaggregated. To migrate hot pages from disaggregated memory to local, we employ the kernel built-in mechanism AutoNUMA. More specifically, we tweak the selection criteria of hot pages of AutoNUMA to prevent the saturation of the bandwidth offered by ThemesisFlow. AutoNUMA, to identify hot pages, performs sequential frames of poisoning the memory pages. At the end of each frame, it selects the hot pages by applying a most recently accessed criteria. However, we want to prevent the saturation of the ThemesisFlow bandwidth, and for that reason, at the end of each poisoning frame, we introduce a variable hot threshold. If the access time of a page is lower than this threshold, it is classified as hot. However, since we know the maximum bandwidth of ThemesisFlow, which is around 100 Gbps, when we detect that the number of hot pages is too high to cause saturation of the bandwidth, we increase the threshold and instruct AutoNUMA to proceed to the next poisoning frame. To make enough room to migrate hot pages identified by the AutoNUMA mechanism when the local memory is depleted, we tweaked the page replacement algorithm of Linux to migrate the pages that it identifies as cold to the disaggregated memory instead of swapping them out to the disk. With these two mechanisms in place, we created a memory tiering between local and disaggregated memory where the hot pages will be on the former and the cold ones on the latter. In the previous slides, we described how we integrated disaggregated memory into Linux NUMA memory policies and thus putting the Linux kernel in charge of how and when to use disaggregated memory. However, the memory needs of a workload vary over time and may exceed the available memory of the node. To address this issue and guarantee that applications always have the resources they need, we introduce the last piece of our system software stack, which is a cloud memory orchestration stack. This stack monitors the state of each node and scales the amount of the attached disaggregated memory according to the current memory pressure of the node. More specifically, it includes two system services, the data exporter and the memory agent service. The data exporter is responsible for collecting and exposing node-level metrics such as memory usage to cloud orchestration stacks such as Kubernetes. When the registration stack detects that the node is either under memory pressure or has a large surplus of attached disaggregated memory, it instructs our memory agent service to modify the state of the node accordingly. In the context of this work, the disaggregated memory pool is simulated by the disaggregated memory offered through the Themesis flow prototype. The hardware setup of our evaluation comprises of two AC922 servers, which feature all the necessary hardware in terms of FPGAs and network links to support the Themesis flow prototype. In terms of hardware characteristics, each of the AC922 server features a dual-socket Power 9 CPU with 16 cores and 4 ways simultaneously multithreading, a total 500 GB locally installed memory, and a Micron 5100 Pro SSD drive. In our evaluation, one server has the role of the compute node, and the other one is the memory node that actually represents the disaggregated memory pool in our experiments. Since AC922 is a dual-socket server, the overall memory is divided in half and is exposed alongside the CPU cores of each socket into two different NUMA nodes, the NUMA node 0 and the node 8. For the needs of our evaluation, we vary the memory size of node 0 from 8 GB to 20 GB. This is achieved via the device tree built by the SkiBoot firmware. That said, our evaluation features in total 6 configurations, which we materialize by using the Linux cgroups mechanism. In the local and the remote configurations, the Linux kernel allocates memory only from local and only from disaggregated memory, respectively. In the hybrid and the policy configurations, instead, the Linux kernel allocates memory from both the local and disaggregated memory. More specifically, allocations start from the local memory and fall back to disaggregated memory as soon as the local memory is depleted. The policy configuration is similar to hybrid, but it also supports memory pages balancing with a customized version of AutoNUMA and page replace algorithm of the Linux kernel presented some slides before. As a result, pages classified as hot get migrated to local memory, while pages identified as cold are migrated to disaggregated. The swap and the Z-swap configurations are identical, except for the latter. We also use the Z-swap kernel mechanism alongside with the swap kernel mechanism for balancing pages between local, memory and disk. Note that in all configurations, approximately 4 GB of local memory are pre-reserved by critical operating system services. In terms of applications, we choose to include 4 categories in our evaluation. For the first category, we choose to emulate a service similar to Travis that will get notified by a key frontend such as GitHub and proceed to compile their corresponding repository. In our evaluation, we emulate such a Travis batch job by running a parallel build of the Linux kernel. As the second category, we evaluate the performance of simple storage services that host large datasets used in AI training workloads. More specifically, we modified Ceph, which is an open-source distributed storage system, to keep all the objects in memory. To extract the performance under all configurations of our evaluation, we uploaded the ImageNet dataset to our custom Ceph system and we trained against it the ResNet 50 model using 4 NVIDIA P100 GPUs. Given that popular social networks generate hundreds of terabytes of new data per day, evaluating the performance of searching large-scale graphs goes without saying. For that reason, we also include in our evaluation Graph 500 that performs a breadth-first search in a large undirected graph. Also, because of the convergence of high-performance computing with cloud computing, we also include LULESH, which is a hydrodynamics physics simulation. Our evaluation is divided into 2 parts. In the first part, we run each application in a standalone fashion and we evaluate its performance for all configurations with a limited amount of local memory, only 8 GB. Also, we will quantify the impact of the local memory size to the hybrid and policy configurations by running and extracting the performance of each application for various sizes of installed local memory, ranging from 8 GB to 20 GB. The first application is the Linux kernel compilation. We built the Linux kernel using 64 threads and we noticed that the compilation features multiple short-term memory allocations that sum up in a 14 GB memory footprint. The left chart depicts the performance of the Linux kernel compilation for all the configurations, while the right chart shows the performance only for hybrid and policy configurations under different sizes of installed local memory. To this end, when the application memory footprint exceeds the available size of the local memory, it utilizes disaggregated memory. The first observation here is that the policy, because of our mechanism that balances hot and cold pages between local and disaggregated memory, achieves 31% better performance compared with the hybrid configuration. Also, it is 62, 63 and 83% faster than the remote, swap and Z-swap configurations respectively. Also, we observe that the Z-swap configuration is the less performant of all configurations. This is because of the aforementioned short-term allocations that the kernel compilation exhibits, which result in the Z-swap adding a considerable overhead before getting the page from the swap mechanism when the local memory is depleted. Also, increasing the size of the installed local memory is not affecting the performance of the policy configuration, which even for 8 GB of local memory matches the local configuration. The next application is the in-memory object storage service. More specifically, our custom chef system reaches 136 GB of memory footprint, which is actually the size of ImageNet dataset. When we have only 8 GB of installed local memory, we observe that the policy, hybrid, and remote configurations match the performance of the local one. This means that the performance characteristics of the disaggregated memory offered by the Themesis Flow prototype are not causing any degradation for this application. That said, the swap and C-swap configurations are 19 and 11% slower compared to the local configuration. As expected, increasing the size of the installed local memory for this application is not affecting the performance of the configurations that utilize disaggregated memory. In our evaluation, we ran Graph 500 application with 64 threads, and we use the toy size of the graph that results in a 24 GB memory footprint. For this application, we observe that the performance characteristics of disaggregated memory are significantly degrading the performance of the application, and as a result, the remote configuration is 599% slower compared with local configuration. The balancing of the memory pages is the reason that the policy outperforms both the hybrid and the remote configurations by 26 and 54% respectively. However, it still remains 224% slower than the local. Moreover, for the swap configuration, the Graph 500 execution hasn't finished in 4 hours, and even worse, for the Z-swap configuration, Graph 500 was getting killed by the out-of-memory Linux manager. When we increase the size of local installed memory, we observe that the performance of both policy and hybrid configurations is improving. More specifically, with 20 GB of local memory, we see that the policy is only 9% slower compared to the local configuration. However, hybrid, because there is no balancing of the pages, remains 98% slower. The last application in our evaluation is LULESH. We ran LULESH with 64 threads and we set the problem size to 350, which results in an average memory footprint of 25 GB. To this end, because LULESH exhibits large memory allocations followed by immediate deallocations, the memory footprint reaches a maximum of 38 GB. Similar to Graph 500 here, we observe that again the performance characteristics of disaggregated memory affect the performance of the application. More specifically, the remote configuration is 846% slower compared to the local configuration. Once again, our balancing mechanism improves the performance of the policy configuration by 45 and 50% compared to hybrid and remote respectively. Again, this is not enough to match the performance of the local configuration. For the swap configuration, LULESH execution lasts almost 2 hours, and similar to Graph 500, for the C-swap configuration, the application is getting killed by the out-of-memory Linux manager. Although increasing the size of the installed local memory improves the performance of both hybrid and policy configurations, we observe that when we reach the 20 GB local memory, both configurations offer the same performance. This is because of 2 reasons. First, the static memory footprint of LULESH fits in the local memory, and thus the performance of hybrid improves significantly, but also the balancing mechanism is not as effective against the short-term large allocations and the allocations of LULESH. Moving on to the second part of our evaluation, we evaluate the over-provisioning of a node. Specifically, realistic cloud computing workloads are characterized by multiple applications encapsulated in virtual machines or containers that share the available computational and memory resources of the physical node. In contrast with the previous evaluation where we run each application in a standalone fashion, here we keep assigning different applications on the same node as long as it has available CPU resources. Also, we fix the amount of local memory closer to realistic deployments at 64 GB, and we include our disaggregated memory cloud orchestrator stack. In this slide, we present 2 charts with the policy configuration. More specifically, the top chart shows at runtime the socket utilization, and the bottom one the utilized and the total available memory for both local and disaggregated memory. The x-axis of both charts is aligned and represents the evolution of time in seconds. At 0 seconds, we start the execution of ResNet training, and we see that as the time passes by, the consumption of local memory increases because the chef system loads in memory all the objects that the ResNet training is touching. At time point t0, our memory agent attaches the first chunk of disaggregated memory because the utilized memory footprint exceeded the threshold. At time point t1, the local memory of the system is exhausted and all future allocations will fall back to disaggregated memory. At T2, we start the Linux kernel compilation, which doesn't cause another memory disaggregation attachment by our memory agent. However, at time points T3 and T4, where Graph 500 and LULESH applications start, we observe that our memory agent attaches more disaggregated memory to alleviate the pressure caused by each application. During the execution of all benchmarks, we observe a jigsaw pattern, which is due to the allocations and deallocations of LULESH. At T5, 3 applications have ended and only ResNet 50 training is still executing. We observe that when the last application of them ended, it created some free local memory, which is again getting reserved by the migrated hot pages of the Ceph system. In this chart, we present the execution time of each application in this node over provisioning scenario for all configurations. To this end, we didn't include the swap configuration because of the out-of-memory problems it exhibits, and also we excluded the hybrid one because it has the same performance as the remote, since all the local memory is initially reserved in this scenario by the Ceph system through the ResNet 50 training. As expected, the local configuration outperforms any other configuration. The second most performant configuration is policy, which is on average 13% slower compared to the local, but 46 and 57% faster compared to the remote and the swap configurations respectively. Noticeably, except for the Linux kernel compilation, remote is faster by 34% on average compared to the swap configuration. These results indicate that introducing and exploiting disaggregated memory through our system software stack can yield comparable performance level to local, as well as effectively increasing the CPU utilization of a node under memory pressure. In this video, I presented a holistic system software integration of disaggregated memory. Based on our evaluation, we proved that the disaggregated memory can be seamlessly integrated into a Linux-based system, that a software-based memory balancing mechanism can improve the performance of disaggregated memory. Also, the disaggregated memory offers, without any balancing, offers better performance compared with traditional disk-related approaches. And lastly, for scenarios with limited amount of local memory, the software-based balancing is not enough to mitigate the performance degradation for some applications due to disaggregated memory. In the future, we plan to explore how to exploit hardware support for identifying the hot and cold disaggregated memory pages, and if we can use high bandwidth memories deployed close to the CPU for caching this disaggregated memory data. Thanks very much, and if you have any question, please join the Q&A session.